Okay, so this is our part 3 of the lecture. Now we'll talk about structural responses. Okay, so structural responses, since there's an external force, so if this is your structure, then let's say a beam, then you have supports, for example, then you have external forces. Once the external forces are subjected to the beam, then what happens, or what is the response, or what is the response of the structure of the beam itself? So we can quantify the response in terms of um, internal loads. Okay, so we can quantify that in terms of internal loads and deformations. Okay, so if you try to draw it in 3D, this is the beam. Then we are having these flexural loads. But if you cut the section, if we cut a section, let's say right here, now what we'll see is that we'll have stresses, force distribution. Okay, so let's make it black. So meaning this, if you try to look at it in this view, what you'll see is a force distribution. Okay, so these are internal loads. And then deformation also exists. So again, if when we talk about internal loads and deformations, then we still think about three-dimensional movements as well. So rotation, or moment reactions. I mean, not moment reactions. Internal bending moments. Okay, so that is another reaction would be, for example, if we have forces right here. Let's say we have axial force, external. Okay, so if we have external axial force, then we'll have some internal axial force. Okay, so this one probably we can just draw it like this, internal moment, instead of distribution. Okay, so we have axial force moment, and what if you have, oh sorry, since this is a beam, then there will be a shooting forces as well. Okay, so it's gonna be shooting forces. Okay, so that's V. So in some cases, if there's no actual external axial force, then you will not have this actual internal loads. Okay. Okay, and another response is the deformation. So meaning, once you apply an external load, then you'll notice a deflection. Okay, so let's say this is a deflection. Okay, so we have also terminologies for this. So let's say this is the initial state, but then after the external force acts on the structure, then you'll see a deflected shape. So if you use the term deflection, referring to this translations. So it's like along translation along y or translation along x. That's what we call deflections. And we use the term slope if we are referring to the angular, or let's say the rotational movement of the point, then that's gonna be slope. Okay, so the topic on solving these deformations is discussed in the subject of strength of materials, like for example beam deflections, how to solve that. All those in structural analysis subject, It's also discussed, but I'll just refer you to the uh, you can you can find a lot of beam formulas in beam design tables, say beam design tables by I think this the NDS. So you can find that, or other textbook they have that beam design, complete beam design table. So if you're dealing with beams, you just go to these beam design tables to find out the, let's say, the maximum moment, the maximum shear, and the deflections and stuff like that. Okay, so there's also a topic on the rules on sketching the deflected shape. So we'll discuss it here. So the deflected shape, for example, we have what's the deflected shape if it's a roller or a pin or a fixed support. So for rollers, since rollers have let's say support reaction like this, then doesn't allow to um, deflect. I mean to actually, yeah, at this point. So let's say we have a beam here. So if there's an external load, then it's not allowed to. I mean, this point is not allowed to go down or go up. So meaning that the deflection is, okay. By the way, the symbol of, sometimes they use the symbol like this, delta, the small delta, for the deflection, and then this is the slope, or we'll just write it here, slope and then deflection. Okay, so for the deflection, that's 0, and then for the slope, since it allows rotation, then that's gonna be depending upon the value. So we'll just say theta. Okay, so for a pin, it's also the same. Okay, so it's just the same. For fixed support, since at this point it doesn't allow rotation, then meaning that the rotation or the slope at this point is 0. Okay, so something like that. Okay, so that's it. Then for fixed connected joint, so for example the portal frame, so let's say it's a fixed connected joint, then if it deflects, then it's something like this. Okay, so it remains this joint uh, it's not deflect along the y or along the x. Of course, what I mean is the the relative the relative joint. Okay, so we have 0 here and then theta. Okay, so that's for fixed connected joint and pin connected joint. Oh, sorry. For the pin connected joint, the deflection would be different. Okay, so anyways, you can refer to the strength of material text or structural analysis textbooks regarding this. Um, I don't have plans to have exercises regarding this. Just an overview. The main point of this lecture is so that when we use the structural analysis software, then we'll be able to understand this these things. Okay, so now let's move on to the fundamental relations. So in any structural problems, the mental relations, we need the equilibrium equations. Okay, so meaning that the equilibrium equations must be satisfied, and then the compatibility conditions must be described. Okay, and then another one is the force deformation relationship must be characterized. Okay, so these are the guiding principles structural in the analysis of structures. So meaning that in any problem, the equilibrium equations must be satisfied. So when we say equilibrium equations, then we should think about the forces. So we use, like, for example, summation of forces along x, y, summation of moment along the z must be equal to 0. So I mean that's gonna be there's no acceleration. That's the point here of equilibrium. Doesn't mean technically that doesn't. I mean equilibrium doesn't mean that it's not moving. Although in structures that's the case, it's not moving. But a more precise description or definition of an equilibrium is that there is no acceleration. So summation of force equal to ma, if you recall from Newton's second law. Okay, so the next thing is the compatibility condition. So I say compatibility, that means or that refers to the geometry of deformations. So meaning that the displacement of the structure of each member must fit together. So or we can say that the displaced geometry or the deformed geometry must be still, for example, um, if it's a joint, a pin joint, for example, the trusses. So it still fits together. I mean, if the member is connected to, okay, I'll just draw it like this. Let's say, like, so if the deformed shape is like this, let's say it moved to here at this point, so that must still be three of them, right? And then force deformation relationship, let's say the from the actual equations, the deflection is equal to p, uniaxial deflection, PL over AE. So this is the deformation, then this is the forces, internal forces. Okay, so what's the relationship? It is related to the actually the stress strain relationship by Hooke's law and stuff like that. So it must be characterized. So these three conditions or fundamental relations really applies in any structural problems. Okay, so now let's move on to the determinacy and stability of structures. So let's say determinacy. Okay, determinacy and stability of structures. Okay, so determinacy is basically it relates the unknown forces and the available equilibrium equations. Okay, so how many equilibrium equations do we have? We have three, right? Summation force x equal to 0, summation forces y, and then the moment is equal to 0. Okay, so meaning that we only have three equations. So if the number of the unknowns are greater than the equilibrium equations, then that's the term there is we have an indeterminate structure. But if it's less than, then we call it less than or equal. That's determinate structure. Okay, so for example, we have this beam. Sorry, so let's say this beam, we have a pin and roller support. Okay, so if it's loaded, for example, it's loaded, then if there's an external loading, recall that it must develop, support reactions develops. So since this is a pin, recall that we have two reactions for the pin, and then for the roller we have only one reaction. Okay, so how many equations, how many unknowns do we have? So let's say this is point A, for example, so AY, AX, and then BY. Okay, so let's call this point A and then point B. So meaning we have three equations, three support reactions, and we have three equations of equilibrium. Then it means that we can solve that using them. We can solve the forces and stuff like that using the equilibrium equations alone. But for, let's say, our beam that's let's say fixed. Okay, that's a fixed beam, and let's say under external loadings, recall that we have, say, AX, AY, and a moment. Say so moment here, the same thing, moment along B, X, and BX and BY. Okay, so how many support reactions do we have? We have three. Three on this side, three on the other side. So six all in all. So we only have three equilibrium equations. Then we cannot solve it. So that's where the compatibility conditions and the force deformation relationship will come into play in order to solve the problem. Okay, so indeterminate and determinate structures, how do we know that it's we have a criterion? So we have a criterion for the trusses and beams and frames. Okay, so for trusses we have B plus R is equal to 2J. If it's equal, then that's gonna be statically determinate. And then for beams and trusses, it's gonna be R, okay, greater than 3 and stuff like that. Okay, so the reactions plus the number of members. Okay, if it's equal, then that's statically determinate. So for beams and trusses, this one, sorry, I guess this one should be equal. So if it's equal or less than, then that's going to be the support reactions. If it's less than the 3 times the number of parts. Okay, it's all explained in our lecture handouts. Okay, then that's going to be statically determinate. Okay, so let's have an example. Let's say for the beam. So if we have, let's say, a fixed beam and then a roller support. Right. So we have, let's say, roller support here. So how many reactions do we have? 1, 2, and then this one, since this is a fixed beam, then that's gonna be, okay, so 1, 2, 3, 4, 5. So the number of R, so let's say R n, and then our criterion. So the number of R is reactions 5, and we have one member. So this is one street member, so that's gonna be so times 3n, so that's 3. So meaning that 5 is greater than 3. So meaning that's indeterminate. Okay, indeterminate to the second degree. Okay, second degree. Okay, so for the frame, for example, so if we have so let's put an internal hinge here. Okay, so we have 1, 2, 3, 4, but since it's an internal hinge, then that's another. Okay, so we can have a cut here, showing only this side. Sorry. So it will show only this side. So we have reactions here and then reactions at the joint. Or if you try to look at this side, then that's the same. So basically, this force is the same as if you are trying to look at the reactions. If you're trying to look at the right side, so they're just the same. So if you count 1, 2, 3, 4, 5, 6, so we have 6. We have okay. So since this is a rigid joint, then say this is just one member. Okay, so one member, so 1, 2, so 2 times 3, 2 times 3, that's 6. So 6 is equal to 6, and that's gonna be determinate. Okay, so again, our goal here is to use the software for structural analysis. So meaning that this this stats right here may not be or can't be directly applied, but the principle. Okay, but the principle, we need to understand these principles. Okay, so I'm not gonna emphasize much about this. It's already taken up in, or let's say, strength of material class or mechanics of engineering statics. Okay, so now let's move on to the overview of the different methods for analysis. So we have, as I've been emphasizing that structural analysis is something like, it's more about the methods, the basic principles, of course, and then the various methods for the different types of structures. So in our last part of our lecture handouts, we have an overview of the different methods. So we have, for example, the truss. Truss. How do you analyze a truss? So we use the most common ones, especially for determining truss. We have the method of joints and method of sections or sections. But of course, that only encompass the forces. So what if you want to analyze or determine the deformations? Then you'll need other methods such as the virtual work methods. Okay, so for beams, we have like moment area. Okay, moment area methods. What else? Okay, let's say the beam deflections, etc. Okay, so it's all about the methods. For frames, also the same. Now let's highlight the indeterminate structures. Okay, so for indeterminate structures, so let's discuss the difference between determinate and indeterminate first. Okay, determinate and indeterminate. Okay, we have said that determinate structures you can just apply the equilibrium, right? But for indeterminate you can't. You need other relationships like force deformation relationships or and the compatibility conditions and stuff like that. But a difference in this too is that indeterminate structures, if you try to consider this, let's say this beam, fixed-ended beam. Now, if this is loaded, actually the moment diagram of this beam would be like this. Whereas for fixed, let's say for these indeterminate structures, we have a moment like this. The value here is, I think that's, if I remember it correctly, that's WL over 8. Whereas here, you have a moment that's like it's like I think WL over okay, so I think this is WL squared over 8. Whereas here WL squared, that's negative. We have negative WL squared over 12. Whereas this one, the value would be WL squared over 24. Okay, so meaning that the stresses, for the stress, we have the advantage of indeterminate structures is that we have smaller stresses. So meaning that if we design a beam, let's say a reference concrete beam, for example, we need to take the loadings, then the size, if we base on this, if we base on this value of the moment, then we will have a result that is let's say a larger beam. Whereas here we'll have a smaller value. Actually, not that one. I think this one. It should be it. Okay, so you'll have a smaller you have smaller stresses, so meaning that you'll have a smaller cross section. So if your cross section is small, then you'll have a intuitively a lower cost for the materials. Okay, another one is that the advantage of indeterminate is that for example, this is the external loadings, and then there's a deflected shape. So in terms of deflected shape, or we can relate this deflection or deformation in terms of the stiffness, we can say that indeterminate structures have greater stiffness. Okay, so why? Because the value of here, so since this is fixed, then recall that we have a zero deflection at that point, and we have a smaller value of this say smaller value of these deflections. So the deflection is I think delta max is WL squared or 384 EI. Okay, so that's the moment of inertia, the moment of inertia, and then the Young's modulus. Whereas here, the deflection, we have WL squared, actually times 5 times. Okay, 5 times WL squared, 384 EI. Okay, so we have greater stiffness for indeterminate structures, and we have smaller stresses. But the problem is, there are also disadvantages. Like, for example, there's a temperature factor that, or a temperature parameter. Let's say we have this fixed end. So recall that you if there's something like a temperature, a significant temperature change, then there's a there's temperature expansion, or let's say thermal expansion of the material. So meaning that it is trying to push this support. So meaning it is inducing stresses at that support. Whereas for determinate determinate structures, okay, so if let's say there's thermal expansion, then it will just move. It is just free to move. So something like that. Okay, so another one is with regard to the support settlements. You can just read it in our lecture headouts. Right, so in our next video, or probably we'll do video conferencing regarding the use of the software. So um, okay, so I guess that's all for now, and I'll upload the links for our I mean for the software that we'll use. So it's actually a free software, and it's really good software, and I've tried a lot of problems, um, and it can solve indeterminate ones. It can show deflections. It can show um, okay, I'll just write it down. I think it's RISA to the education. Okay, education version. Okay, so although it's just 2D, but it's really good software, I guess, and it's really appropriate for our class. Okay, so um, see you in the next video.